Hello everyone, thank you for attending my presentation. My name is Andreas Michael, and this is actually the third year in a row at which I'm presenting at EAGE the EAGE annual conference, and I'm very happy to be doing so. My paper number is 928 on the Near-Wellbore geometry of hydraulic fractures initiated from horizontal wells. The Near-Wellbore hydraulic fracture geometry is to a very big extent determined by the orientation of at which the fracture initiates with respect to the wellbore. In this case, we are talking about horizontal wellbores, so the fracture can assume two extreme orientations. The first one is longitudinal to the wellbore, axial, in a plane axial with respect to the wellbore, and the second one is transverse with a plane orthogonal or lateral with respect to the wellbore. On the right here we have a picture from one of the laboratory tests on highly concentrated gelatin blocks I performed during my master's degree when I was at UT Austin. Using dyed glycerin for fracturing fluid, and we see two longitudinal fractures indicated with the red arrows and one transverse fracture initiating between them. The orientation at which those fractures initiate depends on the stress state at the near wellbore vicinity, right by the wellbore, rather than the far field in situ stresses. That implies that the old adage that if you drill your wellbore or horizontal parallel to the least compressive stress, say SH mid for a horizontal well, does not imply that you will automatically get transverse fractures. You need a little bit of a threshold, and that threshold is varying. A little bit of anisotropy won't do it. It's basically easier to get longitudinal fractures rather than transverse fractures. And now when I say you are going to get longitudinal fracture initiation, it does not mean that if you go far away from the wellbore, you are going to see longitudinal fractures. Those longitudinal fractures that will initiate will stay within the near wellbore vicinity. They will end prematurely, or they will reorient to become transverse as the far field stresses take over, as the fracture propagates away from the wellbore. However, these are beyond the scope of this study, which focuses on what happens in the near wellbore region. Now, if you get longitudinal fractures that terminate in the near wellbore region, you are going to have some negative completion and production related implications. You are going to get early screen outs, and you are going to get low post-stimulation well performance. Here I have at the bottom a schematic from a microseismic study presented at Barry and Miskini's paper from 2015. And we see yellow fracturing fluid from the first stage appearing in stages 2 and 3, moving laterally across stages basically. And the same thing happens with red fluid from stage 2 and blue fluid from stage 3. This lateral movement was attributed to longitudinal fracture initiation, which stayed within the near wellbore region. And the result of that is near wellbore fluid tortuosity, and that's what will eventually trigger the early screen out and the low post-stimulation well productivity that I mentioned earlier. Now, I spent my entire PhD trying at LSU, trying to develop a complete orientation criterion for the fracture initiation from such wells, perforated wells. And I started from an analytical physics-based core. To do that, I basically reduce the problem to that of one well-bore, cylindrical well-bore, intersected by orthogonally by a smaller but also cylindrical perforation, both pressurized at the same pressure. I used a technique first presented by a 2000 paper called by Hossein and Rahmans from an Australian university, where he suggested that if you ignore the perforation, you can use the Kirsch analysis from 1898 to evaluate the stresses at the well-bore radius. That would be the tangential stress sigma theta theta, shown by the red arrow here, the axial stress sigma yy, shown by the blue arrow here, and the green radial stress out of the plane of the screen, as you see, sigma rr. Then you can use those two values, sigma theta theta and sigma yy, to do a second Kirsch analysis for the base of the perforation, the intersection point between those two cylinders. That is the presumed location of fracture initiation. And when you do that, you can evaluate what I call here sigma theta theta p, the tangential stress around the base of the perforation. And the tangential stress at this point here, indicated by sigma theta L, is the stress that you need to overcome in tension to generate longitudinal fracture initiation. And the tangential stress at this point here, indicated by the blue sigma theta T, is the stress that you need to overcome in tension to generate transverse fracture initiation. Hossein did that for ignoring pore pressure and ignoring the tensile stress of the rock. I incorporated those in my papers, I think 2018 and 2019. Then I used a numerical model, a full-fledged three-dimensional numerical model, to evaluate the validity of those closed form expressions, and found that they don't match the exact the closed form expressions from the analytical code does not match the exact true three-dimensional solutions from the numerical model. And now I use that model to evaluate linear correction factor sets for 7 different shale plays: the Barnett, Bakken, Fatesville, Haynesville, Marcellus, and Niobrara from the United States, and Vaca Muerta from Argentina, in order to make the closed form expressions match the numerically derived solutions. So these linear correction factor sets are presented in this paper, and that's its main novelty. Now, here we have a plot of the way those longitudinal and transverse fracturing stresses vary with well-bore pressure. Remember, in a stimulation treatment, hydraulic fracture stimulation treatment, you're going to increase the well-bore pressure until you reach the breakdown pressure. That's where more or less when fracture initiates. Actually, it will initiate a little bit before the breakdown pressure. But we see with the solid, with the red lines, the longitudinal fracturing stresses. The solid line indicates the side of the well-bore, parallel to SH max, let's say. And with the dotted line, we have the top of the well-bore, parallel to SV. That's for the Barnett shale. With the blue lines, it's the same thing, but for transverse fracture initiation. And looking at this plot, we can see 2 criteria that need to be satisfied for us to get transverse fracture initiation. And that is, 1, we need to have the breakdown pressure staying within the breakdown pressure window. That is indicated by the yellow shaded region here. And the breakdown pressure is a Wellbore pressure value, so we read that from the x-axis. If that value is within this yellow shaded region, you are gonna get transverse fracture initiation because the transverse fracturing stress will be more tensile than the tensile stress of the rock. If the breakdown pressure is higher than these values outside this yellow region, you are going to get longitudinal fracture initiation because the longitudinal fracturing stress is more tensile. Remember, hydraulic fractures are tensile failures from the perforation base, according to our assumptions. This breakdown pressure window, as I called, is a good criterion when it comes to practitioners because they do have some control on it through the injection flow rate. For a given in situ stress, you can suppress breakdown pressure if you keep the injection flow rate low. The lower you keep the injection, the higher you bring the injection flow rate, the higher the resultant breakdown pressure will be. So if you keep it low, you might be able to keep the breakdown pressure within this region and get transverse fracture initiation. The second criterion that needs to be satisfied is a little bit more complex. It's called the critical tensile strength. And that is here we have 4 intercepts between the lines and the vertical axis. The most tensile of those 4 intercepts will be the value of transverse fracturing stress at Wellbore pressure equals 0. At this point, you will, this signifies what I call critical tensile strength. If the tensile strength of the rock you are trying to fracture is lower than this value, you will never get transverse fracture initiation. I don't care how low your breakdown pressure is. This is not to the control of the practitioner as much as the breakdown pressure, because there is nothing you can do to change the rock that you are trying to fracture. However, when it comes to experiments, it does matter because sometimes you do have some control in the laboratory. If you cannot get the breakdown pressure within certain limits, maybe you want to play a little bit with the tensile strength of the material that you are trying to fracture, if that's something synthetic. If that's natural rock, not really. Using this analysis, that's the second novelty that is coming from this paper, is I came up with an optimization scheme using oriented perforating. Oriented perforating is when you strategically perforate your wellbore at a single direction or a single phase only, and you do that to achieve either promotion of transverse fracture initiation, which will suppress near-wellbore tortuosity, or to minimize the breakdown pressure. If transverse fracture is not possible, then the best you can do is get those longitudinal fractures to start at the lowest possible breakdown pressure so that you minimize the amount of horsepower that you want to have at the field. And this is the flow chart I'm using. It's fairly simple. Basically, you check if the transverse fracture initiation is possible. If so, you choose the perforation direction that will give the lowest breakdown pressure for those transverse fractures. And if one direction will give longitudinal and the other transverse, obviously you are going to use the one that is giving transverse, even though if that would be at a higher breakdown pressure. If transverse fracture initiation is not possible, then you just try to minimize the breakdown pressure for the longitudinal fracture. Now, for a horizontal well drilled parallel to SH mean, the 2 perforation directions that you will consider is the extremes, that is top of the wellbore and side of the wellbore, like parallel to SV or parallel to SH max. That would be the 2 extremes. Anything else would be in between. In conclusion, my model has an analytical core and numerical data-driven correction factors, and is used to calculate the longitudinal and transverse fracturing stresses to accurately predict the near-wellbore fracture geometry, and that would be a proxy to the level of tortuosity that you are going to encounter. Like I said, physics-based core, numerical correction factor set, and they result in simple and effective closed form expressions. Favorable near-wellbore geometry occurs when the breakdown pressure and the tensile strength of the rock are below those threshold values within the breakdown pressure window and below the critical tensile strength. And by favorable near-wellbore geometry, I basically mean transverse fracture initiation. And of course, the field practitioners can influence only one of those two, the breakdown pressure, directly at least. And then finally, I present an optimization scheme via oriented perforating, where minimum induced near-wellbore tortuosity through transverse fracture initiation will be prioritized over the required horsepower on location, which will take place by minimizing the breakdown pressure of the fractures. If you stay along, later on I will be having another presentation on the scalability of the gelatin experiments I presented at the beginning of this presentation. So you might find that interesting as well. So thank you for your attention, and I will be happy to take any questions. Thank you.